The device shown here reacts to human touch. Well, how is that possible? One way this could work is as follows. Underneath the screen is a series of small metal pads, much smaller than shown here. Some pads are held at higher voltage, in this simulation plus 5 volts, which is a digital standard, and some are held at lower voltage. The pads are electrically charged. Imagine that you wanted to create a small high voltage pad. How would you do it? Perhaps you'd remove some electrons from it so that all that is left is positively charged metal ions. That's essentially what's done here. The electrons are moved to the other pad, so overall electric charge is conserved. Let's adjust the system capacitance to its lowest value so it shows just a single pair of pads. What determines the relationship between charge and voltage? That is, how much excess positive charge do you need to cram in there to get a high voltage? Or, alternatively, how much charge will accumulate at high voltage? The answer depends on the physical geometry of the device in question, and it is embedded in what is called the electrical capacitance of the device. In this case of this pair of small pads, there is roughly 5 picofarads of electrical capacitance, which means that 5 picocoulombs of charge accumulate for every applied volt. We are applying 5 volts, which means that 25 picocoulombs of charge are stored. We can see on the vertical axis of the graph at top left a representation of this. The amount of charge and the voltage, as shown on this graph, obey a linear relationship. The slope of this line is the capacitance itself. So if you have higher capacitance, you'll have a greater stored charge for a given voltage. The diagram at right shows the simple circuit we have here. A battery is shown, represented by the plus and minus signs in a little circle. This is a 5-volt battery in this situation. The 2 pads are shown as 2 plates, and their charges are shown as well. The ground, which really just represents an attachment to the case of the touchscreen device, is shown at right. Let's watch what happens when we hit play. Well, a few things happen. Let's take them one at a time. First of all, we can see on the graph at top left that the total capacitance has dropped, as has the stored charge. By touching near the 2 plates, we have reduced the electrical capacitance of the system. With lower capacitance, the amount of stored charge must go down as well, and charge flows out. In fact, the computer inside the device can detect this flow of charge and from which pads it came from. This is how the computer knows where you touched. The diagram at right shows a second capacitor placed in series with the first. In fact, as you can see from the slider below, the actual human being involved, that is you, have some electrical capacitance, and a very slight charge separation occurs in your body. Since we're talking about picocoulombs of charge, it's not an amount you'd notice. So by introducing a neutral object, our finger, into the system, we disrupt the electric field patterns that exist in the device. This disruption causes charge to flow, which the computer understands. Hope you've enjoyed this simulation.